So this is 8.6, and you're going to need to use your iPad to access a PDF. And so if you go to this, if you type in this URL into Safari, what you'll what you come up with is a PDF full of integration tables. So in this section, what we're going to do is we're going to use these integration tables to find antiderivatives. We really have volumes and volumes of tables and books that will give us antiderivatives for integrals that are just too lengthy to integrate. And so this table represents just a small portion of those, the ones that are really common. So today's essential question then is how to apply the rules in the integration tables in conjunction with other techniques. So in conjunction with U subs and partial fractions and all that stuff to integrate expressions. So the first example is integrating 9 minus 4x squared and the square root of that. And so so what we're going to do is we're going to look in the table, and we're going to look under, the table is organized by type. And so we're going to look under integrals with the form of a squared minus u squared. So a, in these tables, a is usually just a number, and u is a variable term. So in this case, looking in your integration tables, this is a rule 37. So if you look at rule 37, it says this. And so we really just need to identify what a and u are and plug them into the integrated expression. So for this problem, for problem 6, if we rewrite it as a squared minus u squared, we can see that a is 3 and u is 2x. So that being the case, then we have 1/2, and then we have a bracket, a parenthesis, and then we have 2x times the square root of 3 squared minus 2x squared plus, and then 3 squared, arc sign, it's like inverse sign of 2x divided by 3 plus c. So that's just literally the answer. Sometimes we clean it up a little bit, and we evaluate these squared expressions, and just to make it look a little cleaner. For example 14, we're going to look into the tables, and we're going to see it. That's a rule 91 and then a rule 90. So this is actually, we could actually do this one by integration by parts if we wanted to. But once we get to a power bigger than 3, it usually becomes too time consuming. So if we look at rule 91, it looks like this. Natural log of u, which is in this case is x, to some sort of numeric power n. So we have to identify then that n is 3 and u is x. And we see that the answer to that leads to another integral. So that's why we have to do a couple of rules. And so, so plugging in our values for u and our values for n into this answer, this expression, we get x times the natural log of x cubed, and then minus, and then we bring down this next expression, 3 times the natural log of x squared, because that's n minus 1 dx. So now we have to use a rule 90. So if you notice, this setup is u, if we did an integration by part, it's u times v minus v du. So, so we could do an integration by parts here, but integration by parts is just rule 90. So we're going to use that here. So rule 90 looks like this. And so we know then we have an n of 2 and a u of x. And so we're going to go ahead and plug that in then, starting from the beginning. From rule 91, we got this part, x ln x cubed minus, and then we're going to go ahead and stick in n value of 2 and a u value of x. So we're going to have 3 times, because of the 3 up here, and then we're going to have this expression in the brackets. So u is x, and then we have a 2, and then we're going to have a minus 2 ln x, and then we're going to have a plus ln x squared, and then our plus c. So that's the answer for this question. And we can clean that up a little bit by distributing the 3 in the x. So that makes minus 6x, and then minus 6x ln x, and then plus, or minus, excuse me, minus 3x ln x squared plus c. So that looks, that's that final answer there. For 24, we can evaluate x to the 4th sine of x. And again, we could do an integration by parts here, but it would take us 4 times to reduce the power on that x to the 4th. So that's why we're going to use the tables, because doing integration by parts that many times just becomes too time consuming. So looking in our tables, we're going to have to look for a rule that fits this pattern. And we're going to have to jump around a lot. Basically, these rules, 54, 55, 54, 52, all these rules are integrations by parts done for us. So we're going to start out with rule 54, because rule 54 is u to the n sine u. So if u is, and you know, what is this really? This is really integration by parts. So for this first go around, we have a u of x and an n of 4. And so plugging those values into this, you're going to have minus x to the 4th, that's u to the n, that's minus x to the 4th cosine x, plus n, which is 4, to the, and then we have to integrate, because we have an integration sign in this number 54 rule. So we have x to the 3rd, and then cosine x du. So, and so now we look at this form, and we see that in the tables it's a rule 55. So our rule 55 has x to the n cosine, or u to the n cosine u. So it's a cosine rule instead of a sine rule. And so, as you might guess, then you know this rule for a sine had all cosines, so this rule for a cosine has all sines in it. So now we're going to identify that our n is 3 and our u is x. So we're going to plug the x and the 3 in everywhere where we see these. And so we're going to end up with this first part from the first integration, and then plus 4 times the quantity. And now we're going to bring in this. So that's going to be x cubed sine x minus 3, because that's what u is now, or excuse me, that's what n is now, x squared sine x, and then simplifying that, distributing the 4, we have that and that. And I haven't done a plus c yet because I'm really not done integrating. So as you can see, each time we do this, we've reduced it we've reduced that x by a power. So we're just repeating our integration by parts. It's just that we're letting our rules do it quicker for us. So now we're back to a rule 54 because we're back to x to a power sign. So we had to come back to 54. So now our n is 2, our power is 2, and our u is still x. And so now we have this from the first integration and that from the second integration. Now we're going to integrate this x squared sine x. So it's going to be minus x squared cosine x plus 2x cosine x. And so we still have an integration. And so I'm just going to, there's our first integration, our second integration. I'm going to distribute the 12 now, so I have plus 12 and minus 24. And so now we're going to do this last integration here. And so that's a 53, and this is just your integration by parts. and it's just done, you know, completely for you. So if we, our u is still our x, and our n is 1 now, because that's our power on our x. And so bringing down everything we've done already, there we go, and then minus 24, and then so we're going to go ahead and say cosine u plus u sine u. So it's going to be cosine x plus 1, excuse me, plus x sine x. And then now I can finally put on my plus c. So that's the entire answer for that integration. And then I think I just distribute the 24 here. Yeah, that's what I do in that last step. So there's your answer for evaluating this question. So the higher the power, the more times we have to bounce back and forth between rule 54 and 55 to start reducing those powers as we kind of toggle between sine and cosine. Okay, so this one has some interesting characteristics. We've got a 9x squared inside and outside the radical. So when we look at the integration tables, we see that this is a rule 27 that has this form of u squared times the square root of u squared plus or minus a squared, and this is a plus. So my a is actually in front and my u is actually in back, so this is really an a squared plus u squared. So if we identify that a, this is, you know, a squared doesn't have to be a perfect square, and if it's not, that just means a is the square root of a number. And u is 3x, there, because that is 9x squared is a perfect square. So that means then we have, in terms of the groupings that we see, I wrote u as 3x quantity squared, and then I did the same thing inside the radical, and then I chose the plus sign because that's what I have in my original integration. I have a plus sign. And then my a is the square root of 2 quantities, and then I have to square it, so I have quantity squared. So I rewrote it exactly in the form that you see in Rule 27, and now I can start throwing things in place. So I've got 1/8 and then times the quantity, just give myself some space here. So u is 3x, so I've got 3x times the quantity 2 times u squared, so that's 2 times 3x squared. And then I have a plus. I have to take that top sign all the way across. And so I have plus a squared. And then I have a radical with u squared plus a squared in it. Then I have a subtraction sign. And I have a to the 4th, which is root 2 to the 4th, natural log. And then I have, inside the natural log, I have 3x plus, and then I have that radical again of 3x squared plus root 2 squared plus c. So that's the antiderivative for problem 27, and then we can come back and clean this up inside this set of brackets. So the 3x is still up front. This set of brackets is 6x squared plus 2. And then inside this radical, I'm going to put that back at 9x squared plus 2. And then I'm going to simplify the root 2 to the 4th power. That's, oh, I didn't simplify it. That's weird. But if you simplified it, that would be 4. Natural log, and then 3x plus. And then I'm going to change this radical back to 9x squared plus 2 plus c. So these get, you know, lengthy and complicated looking, but that's okay. We're not going to really do much with them other than that. Okay, so looking at this one, we know that e to the minus x squared and sine 2x, they just kind of keep going back and forth between derivatives, and it's not anything we can reduce. So we're going to have to use Rule 85, which looks like this, e to the au sine bu, and where our a is a half, negative a half, excuse me, it's the coefficient of the power, and our b is 2. So this is nice because if you remember back to doing integration by parts on this, we would have had to do this twice to get back to e to the minus x over 2 sine 2x, to bring that over and divide by 2. And that was a real lengthy process. And with our tables, we don't need to engage in that really lengthy process. So, so to get the antiderivative of this, we have e to the au, so that's negative half x, over a squared plus b squared, so negative half squared plus 2 squared, and then times a is negative half sine bu is going to be sine 2x, minus b cosine bu is going to be 2 cosine 2x, and then plus c. And then so we might clean this up a little bit. So we have, on the bottom, we have a fourth plus 4. And there's not much to do to clean that up in the brackets, but we could clean up the denominator a little bit. This is 17 fourths. So we can clean that up a little bit, and we can even clean this front up a little bit. Dividing by 17 fourths is the same as multiplying by 4/17. And I don't know, oh, I see what I did. I brought out this minus sign here. I think that's why I have a minus sign right here. Let's see what happens. Yep. So I took the minus sign out of each term and stuck it out front here. and then I can just have plus terms inside the brackets. So that's probably as simple as the answer can look. For this example, we're going to have not just a straight rule, but we're going to, if we look at the rule here, we're going to have a u sub, so that we can have a 1 in the top and a u in the bottom. So my u sub is going to be u equal theta cubed. That's just like looking at x cubed. We're going to differentiate it the same way. So du then is going to be 3 theta squared d theta. And so we have a theta squared d theta here. That's going to be a 1/3 du. So we're going to substitute that whole thing out with this expression. So, so this expression really becomes this. So here is my theta squared d theta. And that's going to be replaced by a 1/3 du with the 1/3 out front there, and the du inside. And then my u sub here down in the bottom. Now it looks like this. So one thing with rules like this, you notice they have a plus or a minus so that they can kind of do 2 rules in one. And so we have a minus, which means we have the bottom sign, which means as we lay out the answer, we need to make sure to be consistent and take the bottom sign. So our sign in our answer is actually going to be a plus. So we're going to have 1/3 then, and we know u is just u in this case. So we're going to have a tan u plus a secant u plus c. Now we're going to do our u sub and put our theta cubed back in here. So we're going to have tan theta cubed plus secant theta cubed plus c. So that's a integration table with one of our techniques. That's kind of how we mix and match that sort of thing. So our central question was strategies to integrate more complicated expressions. Really, it involves, we have all of these rules, and now we have our tables, and so it's really about identifying those patterns in the tables, and then possibly using a u sub to make the expression look exactly what's in the table, and then cranking out that antiderivative. So at this point you can do section 8.6 using your integration tables, and this is just a 1-day unit. So after this we're done with section 8.6.